Vesper theory is our next topic. Some people look at it and say VSEPR, but I think Vesper is always the way I have heard it. That's fine, doesn't matter at all. In fact, it looks scarier than it is, and knowing that specific term isn't going to help you all at all in the long run. But we're talking about chemical bonding. We're talking about which electrons bonding. Well, those are the valence electrons from the valence shell electrons. And electrons are all negative. What do? They repel, and how do they appear? They appear in pairs. So that's what this really stands for, valence shell electron pair repulsion. And I think its meaning is a little more intuitive than the acronym implies. Electrons have negative charges. They're going to repel each other around a central atom. And the key that we need to work in here is one of the distinctions between Lewis structures and molecular geometries, and that is 3 dimensions. All right. So Vesper theory, pairs of valence electrons tend to be oriented as far apart as possible in 3-dimensional space around a central atom. Oriented as far apart as possible keywords in 3-dimensional space around a central atom. I don't think that this is an unintuitive concept whatsoever, partially because of the way that I've been messing with people this whole time. And what I mean by that is sometimes you'll see a structure like CO2, for instance, all right? So this, I'm going to just mention here, this is intuitive, right? Because mentally we seek balance, right? Uniform distribution of things. So, for example, CO2. You expect to see it like that, have those O's as far apart as possible, versus which you'd see maybe somebody does right angles. All right? Both of these are acceptable Lewis structures, but only one of them matches the 3D geometry, the molecular geometry that we would expect. So we can mention that, right? These are both okay Lewis structures, but one is also the molecular geometry. All right, and when we say molecular geometry, sometimes people will refer to it as Vesper geometry. So that is our topic of interest here, and I'm going to try to highlight one of them. Shows the molecular geometry, and that is this one right here. It's a straight line, okay? And like I said, for this particular example, it might not be super intuitive. I think it's also evident if you look at an example when we saw breaking the non-octet rule, something like BH3, all right? When you draw it, I think a lot of people would expect for Lewis structures, boron, dot, 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 connect those hydrogens like so, or some variation of those 3 hydrogens being like 90 degrees apart with one 180 distinction there. It's not. Now, I, for trolling purposes, often draw it like this: boron, like hydrogen, 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 which is okay as a Lewis structure as well. But I think if you squint at it a little bit, and when you watch ahead in the future, you'll notice that usually for something like this, I will draw it like this, which gives the hydrogens a uniform distribution around that central atom. Those bonds represent electron pairs, and since electrons are negative, they are repelling each other. So it doesn't make sense right here for us to have 90, 90, and 180 separating them. In this case, it just doesn't make sense. But what is most aesthetically pleasing for us also happens to be most accurate in terms of giving our molecular geometry. So in this case, once again, that's the one that gives us our molecular geometry. All 3 of these would be okay in terms of Lewis structures. You can mention that as well. So our goal is going to be trying to save ourselves as much work as possible and dealing with this three-dimensional space. When do things have to be written out in 3 dimensions, and when can we get away with writing them out in 2 dimensions? And there's a very simple answer to that, and that is how many things you have attached to your central atom. And that is going to be the basis of where we go from here. You have probably heard before in math class or somewhere that 1 point determines a point, 2 points give you a line, and 3 points give you a plane. And a plane is 2 dimensions. So we can use that information and say to ourselves that if we have like 2 or 3 total atoms, it has to be something that can be represented in 2-dimensional space. And there are situations where we have more things that can be represented in 2-dimensional space. But once we get past 3 things total, then we're going to start to have to take more things into consideration. Our goal in doing that is going to try to keep things as far apart as possible in 3-dimensional space.